All right, hello and welcome. Good afternoon, I think. Time zones are hard. Anyway, welcome to my talk on IF Bridge performance, and ideally IF Bridge performance improvements, because making things slower is much easier than making them faster. Moving right along, we have to start with the obligatory shameless self-promotion. I'm Christoph, KP at freebsd.org. So I'm a FreeBSD committer. In FreeBSD, I maintain the PF firewall. PF is one of the firewalls in FreeBSD. It was borrowed from OpenBSD. And I've done some things to it, like making it cope with IPv6 fragmentation, improved VNet support. A while ago, I did some performance work on PF Sync. Professionally, I do a lot of embedded Linux projects. Well, ideally embedded projects, but those often end up being Linux things. Recently, I've been doing RISC-V projects, which has been a lot of fun. I thoroughly recommend that if you can get your hands on it, get yourself some RISC-V hardware and play with it. It's very nice. Aside from that, I'm a board member, actually the treasurer for the EuroBSDCon Foundation. The EuroBSDCon Foundation, it may not surprise you to learn, is the foundation behind the European BSD conference. We were supposed to have a conference late September. Unfortunately, the thing. We should have one next year, so September 2021. If you find yourself in the neighborhood, Vienna, it will be in Vienna. If you find yourself in the neighborhood, you should totally come. It's an awesome conference. I'm a freelancer, so that means I'm not for sale, but I can be rented if you happen to be interested. Moving on to further shameless promotion, but this time for other people. This project was generously sponsored by the FreeBSD Foundation. As distinct from the EuroBSDCon Foundation, the FreeBSD Foundation supports the FreeBSD project. It does things like provide a legal entity for non-disclosure agreements, legal support where it's required. They do a lot of financial support for things like conferences, but also specific projects to improve the FreeBSD operating system, including, in this case, the performance improvement for the bridge. You should go visit the FreeBSD Foundation's website. They have a shiny new website. And if you're a grateful FreeBSD user, you should give them some money. It goes to, well, some of it may have gone to me, but most of it goes to very worthwhile causes. Moving on to the topic of the day, bridges, connecting bank to bank or even island to island. No, wait, that's wrong. We're talking about a different kind of bridges, this kind of bridge. Which you might know better as switches. So what does IF Bridge do? Well, it's an Ethernet bridge switch. It links two or more Ethernet interfaces together into a single broadcast domain, which means that if you have interface A and B, packets can go from interface A to B, but that's not all. They can also go from interface B to interface A. Yes, hold your applause. We also support things like spanning tree. There's a beautiful poem about how spanning tree works, and I always forget it. You should look it up. It's wonderful. It also supports things like port mirroring, which is useful when you're debugging things. You can monitor traffic. What would we use the bridge for? Well, it's a switch. It's an expensive switch if you need a computer. It's also a relatively slow switch. Even after all of the work I've done to it, it's never going to be as fast as a dedicated hardware solution. But because it's software, it is more flexible. It can be really useful when you're testing and debugging things. Imagine that you have an embedded board with an Ethernet interface, and you want to see, what sort of traffic comes out of that device. You can conceivably plug two Ethernet interfaces into your laptop, bridge them together, and then you can observe, without interfering with, you can observe all of the traffic that comes out of and goes into that device. Something I've done myself a couple of times for debugging. Primary use case for this is probably in things like VM hosting. Excuse me, I felt a sneeze coming on there. So VM hosting or VNet jail hosting. A little bit more about VNet jails later. I have an entire separate talk about VNet jails and how they are, how we use them in FreeBSD to do things like firewall testing. It's very exciting as well. Or Beehive hosting. Beehive being the virtualization system in FreeBSD. So in this setup, you would have a hosting machine, a nice and powerful server machine somewhere, and you split that up into several virtual machines. Out of these virtual machines, you get a tap interface, so a network connection that goes to the virtual machine. You could bridge those together, and then it looks like your virtual machines are real machines plugged into the same switch. And then you can decide what you do with that switch. You can plug it into the rest of your network by including, the your uplink interface into the switch, into the IF bridge interface, or you can choose to route or NAT between those interfaces. It's software, you have total flexibility in what you want to do. So that all sounds really wonderful, but obviously there's a problem somewhere, because if there's no problem, there's no talk, and I've just been wasting your time, and that would be wrong. So there is a problem, and the title of the presentation probably already gave you a clue. The problem is that IF Bridge in FreeBSD is or was slow. When we test this with packetgen, we find that we can pay attention here. Some of these lines are the number of packets that we transmit. So the first line is the one where we transmit 27 million packets per second. That is transmitted packets. Second line is received packets. So in this setup, we have two machines with two network interfaces each. The two network interface 1 from machine 1 is connected to interface 1 from machine 2, and so on for the other interface. What we do in this setup is on the test machine, we bridge those two interfaces together. The other machine sends traffic into one interface and measures how many packets it gets out to the other interface. Test machine will bridge those as fast as it possibly can, and then depending on how many packets we receive, we know that the system is faster or slower. So we transmit 27 million packets per second, we receive 3.6 million packets per second. That's not as many as we would have hoped. Especially because if we're routing, we can do significantly more than this. I think off the top of my head, that would be more on the order of 8 to 9 million packets per second. We've not actually benchmarked it in this setup, but that's the sort of number I would expect. And switching being slower than routing, that's just wrong. That's not how it should be. In this test setup, we generate 64-byte packets as opposed to the more typical full-sized Ethernet packets that are 1500 bytes long. Why do we do this? Because that's the worst case scenario. Any operational network packets has a fixed per packet overhead, typically has a fixed per packet overhead, which means that larger packets are more efficient than smaller packets. And because we care about, when we're testing performance, we typically look at the worst case. Because if we reduce per packet overhead for small packets, we've also reduced it for large packets, and we will get some benefit of that as well. Not as much as we would for smaller packets, because the overhead is aggregated over more data, but we still get it. When you're measuring these things, it's useful for your problem to be as visible as it can possibly be, hence this. Before we move on, small word on packetgen. Packetgen is a packet generation tool, which probably won't surprise you. But it's built on top of NetMap. NetMap is, according to its blurb, a framework for extremely fast and efficient packet I/O for user space and kernel clients running on FreeBSD, Linux, and some versions of Windows. Clearly, we only care about the FreeBSD version. Essentially, what it is a very, very efficient way of sending and receiving packets. It has some limitations that are not relevant for the benchmark that we're doing here, so we're not going to go into them. But it means that we can send far more packets than we would normally be able to do with things like iPerf. It's fairly common that you go to benchmark network performance, you run iPerf, and you discover that you're not actually bottlenecked on your network performance, but on the efficiency of iPerf going through the entire network stack, starting with a send or a write call in user space, going into kernel space, building your network packet through the network stack, and finally transmitting it. There can be so much overhead that you can't actually see your network performance problem. NetMap bypasses this largely by essentially exposing the network interface directly to user space. You throw a fully formed packet into it and immediately transmit it. There are other talks on the subject of NetMap. I'm horribly simplifying, but the main point is that NetMap is a wonderful thing if you want to send many packets very quickly. So now that we know that there's a problem, it would be useful to figure out where the problem is, because if we want to fix it, we should know where the problem is. How do we figure that out? Well, it turns out FreeBSD has another wonderful tool called PMC Stat. PMC Stat exposes hardware performance counters that live in the CPU and let you retrieve interesting information like, which functions did we spend all of our time in? One of the wonderful things about PMC Stat is that because it uses the hardware counters in the CPU, it has very little overhead. Many other tools, so FreeBSD has an entire suite of wonderful, wonderful diagnostic tools like dtrace, which was liberated from Solaris, or Logstat, which I don't actually know where that one came from. They are very, very useful tools, but they have, to a greater or lesser extent, they have some overhead when they are running. Like running your application in a debugger, it's slower than it is without the debugger. And the problem with that is that it tends to skew your results slightly. It's not always a problem, but it can lead you astray. You may be measuring performance overhead from your measurement tool more than actual performance issues in your code. Because these are hardware counters, they don't really have this problem. You get essentially your full performance while you're running this, and you get a much more accurate picture of what's going on. The output of PMC Stat gets post-processed and turned into what's called a flame graph, for what I hope are obvious reasons. The way you read this is the width of the graph indicates how much time we've spent in an individual function. On the height of the graph is essentially a call stack, which means that if we go to look at this, for instance, we have T4 inter, which is the interrupt handler for the network card that we happen to be using here, which calls into service IQFL, which calls into ether input, which is the input function for Ethernet, which dispatches to a network interrupt service routine, which goes to ether NH input, which is, Ethernet input function, which calls bridge input, so getting packets into the bridge. And then bridge input seems to be spending, it spends a little bit of time in bridge forward, over off to the right of the flame graph, and bridge forward queues packets for transmission, which calls CXGBE transmit, which is a network driver transmit function, so that all makes sense. But we seem to be spending most of our time in a function called MTX lock sleep, which calls lock delay. Delaying things while you're trying to transmit as many packets as possible, probably not a good thing. sleep is a wonderful thing. We should all try to get a sufficient amount of sleep, but not our computers. Our computers, when we want them to do work, they should be awake and alert and working hard, not sleeping like this is doing. So what we want to look at from this flame graph, the obvious place to start looking is, why are we spending time in a function called sleep? And also, what is an MTX? Well, MTXs are mutexes because, typing those 2 extra characters takes far too much time and we're all far too busy or possibly lazy to type those. So what we have is a mutex sleep function. What is a mutex? A mutex provides mutual exclusion, hence the name. Mutual exclusion means that other cores can't access our data structures while we're using them. Why would we want to do this? Well, because sometimes when we manipulate our data structures while we're changing them, they enter intermediate states where they are not valid. And if somebody else tries to walk through that data structure and happens to do it at the same time while we're manipulating it, they might encounter an invalid state, become confused, and then you end up with bad things like kernel panics or invalid data being written to your disk, and everybody has a bad day. To prevent this, we make sure that nobody else can access the data structure while we're changing it. And once we're done with it, somebody else can take the mutex, can go look at the data structure in a consistent state and use it this way. And that's, that has the great advantage of not leading to crashes, which, let's not underestimate that advantage. That's a pretty nice thing to have. The downside of it, of course, is the mutual exclusion bit, is that only one core can do useful work at a time. So we might have this very fancy and expensive 40-core machine with a network card that will very helpfully move packets, spread packets out across different cores, so all of the cores can process them at the same time, and we can go really fast. And then core A gets a packet, and the first thing it does is it acquires the mutex, and then simultaneously core B gets a packet, and it wants to process this packet, and it tries to acquire the mutex, and it can't. It just has to sit there and wait. And that sitting there and wait is this mutex lock sleep that we see. That's where a lot of our performance is lost. Essentially, what it boils down to is that we've paid for a very shiny 40-core machine to transmit packets, and we can only use 1 out of our 40 cores. Kind of a waste of cores, isn't it? So we need to try to, well, before we try to do better, we can look at how this works in code, although this particular example isn't that instructive, so we're just going to quickly skip that one and ask ourselves the question, how can we make this better? Well, obviously, if our problem is that only 1 core can do things at a time, we want to change the problem so that more than 1 core can do a thing at a time. Seems like that would make sense. How can we do this? Well, the first thing to realize is that while I was explaining what mutexes were for, is I said that they prevent us from getting into trouble when 1 core changes something while another core is reading. Well, we could split our accesses up into 2 categories, because reading while another core is reading is safe. We can have as many cores reading a data structure at the same time as we like, as long as no cores are simultaneously modifying the data structure. This is safe. Hence the RW lock or reader-writer lock or read-write lock. We can have multiple readers at the same time, but we can only have 1 writer at a time, and we can have, while we have the writer, we can have no readers. So if we were to change the locking in the bridge so that when we need to read from the data structures, we acquire a read lock, and we only acquire a write lock when we try to write something, we would already have a significant improvement in throughput, because while we're reading, all of our cores can do things at the same time, and it will work. It's only when we try to write something, which in the case of the bridge is things like, we're reconfiguring it and we're adding or removing an interface, or we're reconfiguring it and setting up a monitoring port. Or the much more likely case, we have learned a new MAC address. We have learned that MAC address that a certain MAC address lives on this port, and we need to save this because the next time a packet turns up for that MAC address, we know we only transmitted out this particular port. So that's great. That is great. That would be a significant improvement. And in fact, I have prototyped something like this, and it was a significant improvement. It still means that while updates are being done, we can't actually process any packets. But updates are vastly less common than reads, so that would be a significant improvement. On that subject, the RW lock is actually not the locking system that you want to use. You want to use the RM lock, which stands for read mostly, which is for workloads where we have many more reads than writes. So which is the most common case. So in this case, we would use RM lock. It has essentially the same use as RW lock, but it's faster for read accesses, at the price of write accesses being slightly slower, of course. So that would be one option, but we can do even better. Thanks to the EPOCH system that was introduced in FreeBSD 13 heads, the upcoming release. Well, it was introduced earlier, but it really got into its stride there. We'll go into detail about how that works and how we use it, well, at least to the extent that I understand it, because I don't want to pretend to be to have invented this or to be even an expert in how it all works. This was obtained from the ConcurrencyKit people. ConcurrencyKit is a collection of tools, code for lockless data structures, high-performance concurrent data structures. And from this toolkit, we get a data structure, a list, because the bridge only uses simple data structures like lists, mostly simple data structures like lists. And the CK list, so the ConcurrencyKit list, can be used without any lock at all. That is, as they say it in the documentation, it is safe to use for each safe in the presence of concurrent modifications to the list. That is, we can iterate the list and we can read it without taking a lock while somebody else is modifying it. So we don't even need to stop processing packets while somebody is adding a new interface, while we're learning a new MAC address, things like that. There is still the limitations that writers to these lists must implement writer-side synchronization. That is, we can still only have one writer at a time. So we can, if two cores at the same time learn about a new MAC address, they will still be serialized with respect to each other. So if we have core 1 learning about MAC address A, we have core 2 learning about MAC address B, only one of those two can be done at the same time, but core 3 up to core 40 can keep processing packets, sending them through the bridge without having to wait for core 1 and 2 to get their work done. Yes, that does sound like it would be a great improvement, doesn't it? We use these inside the bridge for three main variables, three classes of data. IF list, which is the list of interfaces that are bridged together. The RT hash, which is the data structure we use to contain the information about which MAC address lives on which port, so that when a packet arrives from MAC address A, we know that we need to send it out port 1 rather than flood it out of all ports. I mean, we could do that and then we wouldn't need to protect the RT hash data structure. We could just flood traffic out, but that would have a different performance problem. Span list is the list of mirror ports. So if we have entries in those in that list, all traffic that passes over the bridge will clone out of that interface. It's mostly a debugging feature. I list this for completeness. For those three lists, there are essentially three scenarios. Iterate, read the list, insert, add new entries to the list, or delete, remove entries from the list. So iterate is a fairly typical scenario where a packet arrives and we need to know which interface do we send it out on. So we go and look through our RT hash list and figure out, do we have an entry for the destination MAC address that this packet has. We run through the list. If we find an entry, we know which interface we need to send it out through. If we don't find an entry, then, typical switch behavior. If we don't know where to send it, we send it out of all ports except for the one we received it on. So we would run over our IF list. Iterate through the list of interfaces in our bridge. When we learn a new MAC address, we figure out that MAC address A belongs on port 1, we will insert it into our RT hash list. Or if we add an interface to our bridge, we will insert it in the IF list. Delete, fairly obvious. When a MAC address entry times out, we delete, we remove it from our list. When we remove an interface from our bridge, we remove it from the IF list. Those are the three main scenarios that we need to cope with. All of them are handled in slightly different ways, and we'll go into some more detail about how that works now. Iterating, reading is the easiest one of all because we don't need to take locks. We can do that on all cores at the same time. We're only reading data structures because we can't go and modify them while we're reading without any further locking taken, but we can just read them. The only thing that we need to remember is we need to enter the epoch. And when we get to delete, it will become clear why this is necessary. But you can compare it to entering the read section on a read-write lock. We can have multiple cores enter epoch at the same time, as many cores as we like. In fact, the way this works in FreeBSD is because we can have many cores enter epoch at the same time, there is no reason to keep the area covered by an epoch small. So by and large, when we receive a network packet on an interface, we enter epoch, we do all of the processing on the packet, figuring out if we need to bridge it, firewall processing, routing it, handing it over to, and then only when we hand it over to the network driver for transmission out of whatever interface it needs to go out, do we leave the epoch again. So we cover quite a lot of that, which is also kind of interesting because what little overhead entering and exiting epoch has, we only do once per packet essentially. The entering and exiting epoch is required to allow deletes to work correctly, which we'll cover in more detail when we get to deletions. The main point here is that we do not take a lock. We can run this on all of our cores at the same time with essentially no speed bumps along the way, so we can really process packets as fast as possible without having to wait. Second scenario is we are inserting new entries. Let's say that we want to add a new interface to the bridge. Remember that we must hold a lock because our CK list structures, we can have as many readers at a time as we like, but we can only have one writer to it at a time. So whenever we insert or delete something from the list, we must take a lock. In the bridge code, we have recycled the previous bridge mutex to do this. So the mutex is still there in the new bridge code. It just doesn't cover as much of the bridge code as it used to. So make sure that we only have one writer at a time. That's why we still have a lock. Another thing that's important to remember is that this lock does not cover readers. So the instant that we insert a data structure in list, it's possible for another core to see it and start reading it. So the main thing that we must remember there is that before we insert this data structure into the list, it must be fully populated with correct and relevant data. That is, if say we add an RT entry, which is the entry that tells us that this particular MAC address goes out of this particular interface. So this data structure obviously has two members. That is the interface and the MAC address. So when we insert one of those, a new RT entry, we fill out the interface, we fill out the MAC address, and only then insert it into the list. Because if we did it in another order, if we left it empty and we inserted it into the list and only then wrote to it, it would be possible for another core to see the new entry, read the MAC address, which would be complete, which would be zeros or random data, or even worse, look at the pointer to the interface that it needs to send out of. This being an invalid pointer, dereferences it, and then you get a kernel panic and people are angry with you. So fill out the structure completely before inserting it, because another thread could use it the instant that we insert it. Not particularly difficult, just one detail that we need to remember. Well, two. You need to lock and we need to do operations in the correct order. Deleting is the complicated one. So, let's say that we want to delete something. We have an RT entry that has expired. We've not seen traffic from this particular MAC address for long enough that we're just going to forget which interface it lived on. To do this, again, we must hold the lock, same discussion as with the insertion, because we can only have one writer to the list at a time. Remember that people can still be reading from that list while we're writing to it, which means that the data structure we're trying to delete might still be being read by another thread or another core at the same time. So we can't just free that memory and use it for something else, because some other core might still be reading that data. So how do we deal with that? We do it by deferring the delete. And that's what the EPOCH system allows us to do. Essentially, because essentially what it does is it tells us when no other core could still conceivably be using the structure that we have just removed from the list. So how do we do this? There's an important order of operations. We first remove the item from the list. Removing the item from the list ensures that nobody else, that cores that start iterating the list after we do the removal, will no longer see that particular entry. So that means that from that moment on, no cores that enter an epoch after that point, we know for sure that they will not see that entry. So the only cores that we still need to worry about are the ones that entered epoch before we removed the item from the list, because they could conceivably still see that data structure. So we have a callback that, well, we have a macro net epoch call that allows us to register callback functions, and they will be called once we know for sure that the data structure is that particular structure is no longer in use by any other core. Once that gets called, we can safely free the structure and start reusing that memory for something else. Important to remember here is that between step 1 and 2, between us removing it from the list and knowing for and that callback getting called, it could still be in use by other threads. So the order of operations is or the way this can happen is core A is running through the list of RT entries. So, or is going to do this. It enters epoch. We remember that at time A we entered epoch. It starts to run over the list of entries. Simultaneously, core 2 decides that it wants to remove one of those entries. So it takes the lock, which it can do because core 1 is only reading, so it did not take the lock. It removes the entry from the list. Now, we don't know in which, if core 1 has already seen that entry or not. So we assume that it has not seen it and it may use that entry later on. Core 2 says, okay, call me, call this particular function once we know for sure that nobody else is using this particular entry anymore. And it goes and it's done with the removal from the list. It's done with the initial work of the delete, but it has not freed the memory. The memory is still around. It's no longer listed in the list, but it's still around. So if core 1 happened to be looking at that data structure, the data that's at that particular entry, the data is still there. It can still safely look at it. And then after some time, once core 1 runs through all of the entries in the RT hash, it will let the epoch system know that it's done by exiting epoch, by calling net epoch exit. At that point, well, potentially, if no other cores are doing anything anymore, the epoch system knows that, okay, the last possible core that could have been using this data is now done with it, so we can call the code to free it. We call the callback, we free the memory, and we continue onwards. Essentially, what we've done is there's now a decoupling between when we remove it from the list and when we free the memory. Might be slightly easier to understand if we go look at a little example. So this is the actual real code. When we remove an RT node from the list, we call bridge RT node destroy. We get the RT node that we need to remove. We assert that we have the bridge lock. Remember that I said we reuse the bridge lock to protect write accesses to our data structures. We no longer protect read accesses with it. We kept the lock to protect our write accesses. So first thing we do is we remove it from the list. Turns out there are 2 lists in the bridge for reasons of efficiency, but the principle is the same. We remove it from the list, we update some counters, but we don't actually free the memory. Instead, we register a callback with net epoch call, where we register the bridge RT node destroy CB callback, and we give it a context pointer so that we know which particular data entry we're talking about. And then this bridge RT node destroy callback function will only get called once nobody is using this particular BRT anymore. Once that's the case, the epoch framework tells us this. We enter the callback and we can UMA-Z free, we can free the memory. And then the memory is free and we're completely done with it. So there is a delay between removing it from the list and removing it from memory. So after having done all of that work, what are our results? Well, we take our flame graph again, using PMC stat again, and you will see that this looks somewhat different. We still have T4 inter, so our interrupt for incoming packets, which still calls service IQFL, which still calls ether input, which still calls netisr dispatch, which calls into ether nh input, which calls bridge input, which calls bridge forward and bridge enqueue, which finally transmits the data. So there's no longer any mutex sleep in here. Now, the thing to remember here, of course, is that these widths are proportional. It means that we spent more of our time in the bridge forward function. Not that the bridge forward function got slower, just that we spent more of our time there. And that's actually what we want to see. We want to see the system spend as much time as possible, as much of its time as possible, doing useful work, rather than sitting there and sleeping on mutexes. Clearly, in this flame graph, a lot more useful work is happening. So we would assume we would also get more throughput. Now, we all know what they say about assumptions, so we should verify this. Running the same test setup, one interface sends packets, the other interface receives packets. What do we see? We now receive 18.6 million 18.637, 18.62, 18.64. Call it 18.6 million packets per second. Recall that before we did this change, we only received 3.9. So from about 4 to more than 18 is, I think you will agree, a fairly substantial improvement. It's times 4.5. I have actually seen results from other people who did a little better work optimizing their setup, or they just had better hardware, where the improvement was even more pronounced than this. So, if you're interested in more details, there is a slide set on the ConcurrencyKit website that explains how this EPOCH thing works. There are videos on YouTube. I would definitely recommend those. This link goes straight to the patch, the single commit that I did to make this change. Well, there were more commits, but they just did some preliminary cleanup. The actual meat of the change is here. We can scroll through this. I'm not actually going to go into full detail here, but we can see the sorts of changes that we did. You may recognize this pattern. This is a delayed callback for when we destroy certain things. We have net epoch enter, net epoch exit. We have another delayed callback for when we delete another type of entries, and well, there we go. Here, when we delete members, rather than we used to free it, but now we net epoch call, and then eventually, when the epoch system decides that nobody is using this particular bridge member anymore, we call the callback and end up in there. And that's essentially the patch set. For those of you who are interested, feel free to go and look at this. It turns out to actually work, so that's useful. Aside from that, I've also done some work on writing tests for this. I've already referenced the VNet system. Networking tests in FreeBSD, a lot of them rely on VNet. VNet is an extension to our jails, which means that the jail has its own IP stack. Think of, well, jails are chroot on steroids. Kids these days like to call them containers. It essentially means that we can have a very lightweight virtual FreeBSD machine. To all extents and purposes, it looks very much like having a FreeBSD machine, except that it doesn't simulate an entire machine. It's just the kernel deciding that you get this slice of resources, you get that slice, and you can't actually see any of the others. VNet means that it has its own IP stack, which means that there's an extremely lightweight way of saying, I want 5 or 6 different machines that can communicate with each other over the network. I would recommend that you go look at some of this test code because it is actually surprisingly easy to write some of these tests. They are very quick to run. Running through all of these tests is maybe 20-30 seconds, and it only takes that long because some of them have waits for timeouts in them to test things. We've got a bunch of different test cases, transmitting packets over the bridge, running spanning tree, adding static MAC entries to the bridge, so statically telling it that this particular MAC address lives on this port, adding monitoring ports in the span test. Inherit MAC was interesting because it references a specific bug, which we can look at if the FreeBSD Bugzilla decides to cooperate. There we go. There was a user who reported seeing issues adding an interface to the bridge, and without going into too much detail, you add the interface to the bridge. This causes the bridge to change its MAC address due to a non-default setting of the user. And changing the MAC address in turn causes FreeBSD to send an ARP entry to make sure that the rest of the network knows that, hey, our MAC address changed. You should know about this. So we send out ARP replies to announce this to everyone. This ARP reply goes out over the bridge. This was the old bridge code, which meant that you needed to take the bridge lock to do this. But because we were handling a change to the bridge, we already had the bridge lock, so we tried to acquire the bridge lock while we had the bridge lock, which is essentially what this panic message says. We recursed on a non-recursable mutex, so we tried to acquire a lock that we already had, which is bad, system panics, and everything breaks. This now works because while we do these changes, yes, we acquire a write lock to the bridge, but we do not need to acquire that lock anymore to transmit packets. So we don't lock against ourselves, and this problem is now fixed, as we can see here. Oh, and we can go look at this patch set, because this presents a good example of how difficult it is to write tests. Yes, this is the entire commit. This is a full test, and you can probably tell that this is add the test to the list of test cases. This is some basic boilerplate setup. We set a description. We reference the bug number. We need to be root to run this test, and then we create a bridge. We create an interface to put in the bridge. We create a jail. We give that jail the bridge, the ePair. We give that, essentially that jail gets two network interfaces, a bridge and an interface to put in the bridge. We set the appropriate system configuration variable to say that we need to inherit the MAC, and then we try to provoke the panic. So assign an IP address to the bridge, add the interface to the bridge, and without the fix to this bug, that panics. With the fix, that just works. So we don't actually verify that everything went well. We just assume that if we don't die in a horrible fireball, that everything went well. And then we clean up, so we delete the jail, we delete the interfaces. Point is, it's omitting the boilerplate. It's 1, 2, 3, 4, 5, 6 lines of shellcode to write this test. I have a different talk where I go into much more detail about this, but I still love these tests. They make life so much better. Because, of course, I wrote all of these tests before I did the change to the bridge. Because then I could run through these tests while I was making changes and see if things panic or not. Delete with members is one of those tests that I added afterwards because I discovered that if we deleted a bridge that still had member interfaces, that it would panic while I was making the change. So you add a test and you don't see... to make sure that you don't regress, rather. I typically run these tests on a kernel that has witness and invariance turned on. Invariants are basically assertions. So throughout the code in the kernel, you will see things like k-assert this, or possibly MPASS that. Actually, if we go back to this patch, I'm sure I can give you some examples. I'm sure there are examples. Oh, there we go. Bridge lock assert is one of those invariants. We assert that when we are here at this point in the code, we must have the lock, or we must be in EPOCH when we are here in the code. Those assertions get compiled out. They get disabled when you run this, when you run a normal release version of FreeBSD, because some of them do have an impact on performance. But while you're developing, they are incredibly useful because they provide early warning of problems. I've mentioned witness. Witness is essentially a lock debugger. It keeps an eye on things like, you lock here, but you already had this lock, so that's wrong. You can't do this. It also provides information about lock order reversals. A common problem with mutexes is you have mutex A and B. And if you don't always take them in the order of first A and then B, you risk ending up in a situation where core 1 takes lock A, and then tries to take lock B, but at the same time core 2 took lock B and tries to take lock A, and neither one of them can make progress because the other one holds the lock that they're waiting for and is waiting for the lock that they have. You have a deadlock and you become unhappy. Witness provides warnings for this. Again, there's a performance impact, so that's not enabled on release builds, but it is incredibly useful during development. If there are any questions, now would be a good time. Well, I say now, not now when I say now, because I'm recording this beforehand, but now when you hear it now. Time is difficult. Just ask questions now, please. Thank you. Hopefully somebody will pause the presentation here, because I have one more slide here with some links to a blog post by the FreeBSD Foundation about this project, and a link to an entry in the FreeBSD journal about this, where I wrote an article on this topic. You may want to read this, you may not. There is other information in the FreeBSD journal. The FreeBSD journal is free, so you have no excuse. You have no excuse to not subscribe to it. That is all. I hope you've enjoyed it. I hope you have questions. I will be around for the questions.